Hello, student. Welcome to today's experiment. Today we are going to talk about experiment C8, and this is linear expansion experiment. So we are going to determine the expansion coefficient for these three metal rods: copper, brass, and steel. So the concept of linear expansion is such that when a material is subjected to heat, it tends to increase in one dimension in length. So when the increase is in one dimension, as we've said, length, then that is called a linear expansion. But when the increase is also in other dimensions, such as area, volume, then that is called a thermal expansion. So the difference between linear expansion and thermal expansion is such that linear expansion, the increase is in one dimension, say length, and while in thermal expansion, we have the change in size of materials. Change in size can be in area, volume, or in, even the density of the materials. So some of the applications of linear expansion experiment, we find that when maybe one wants to fit in the concept of riveting, linear expansion concept is applied, and also in fitting the steel iron on a hose cut wheel, we see that the concept of linear expansion is applied. So today our interest is to determine or measure the expansion coefficient of this metal rod. So we are going to start away by looking at what procedures are needed to set up this experiment, and also we are going to try to see the kind of apparatus that is used or that is needed for this experiment, and then we'll be able to get data, and we will come up with the analysis to reflect our objective, and we shall also compare our result with the standard or theoretical values, and also come up with a conclusion. So the introduction of our study, we find that when a material, e.g. metal, is heated, it increases in length. Now the change in size of materials when subjected to heat is called thermal expansion. The change in size can be in density. A material can change in volume, it can change in area, then that is called a thermal expansion. So in this experiment, a linear expansion of copper, brass, and steel is measured. As we've said, a linear expansion is when the change is along one dimension. So that is the key study point of our experiment. We are going to determine where the coefficient of a linear expansion of these metal rods when they are subjected to heat. So as we've said, the objectives is that we are supposed to measure the coefficient of linear expansion of the three metal rods that we've discussed, that is brass, copper, and steel. Brass, we know that is just an alloy of copper and zinc, and copper is seems to be the material that is known to be the good conductor of heat. And of course, steel is the material that is most preferably used in buildings and also in engineering works. So some of the material that are needed for this study are as follows. We have what we call an expansion apparatus. So this apparatus is used for measuring the expansion of materials in dependence of length. It has various parts, as you're going to see below. It has an inlet and outlet pipe that allows steam to enter and exit the metal tube. It also has a metal tube that holds the metal rod, a dial gauge to indicate the amount of expansion. So this is the dial gauge that will be used to indicate the amount of expansion when the metal rod will be subjected to steam and expands. Then this is the metal tube. This is the one that will hold the metal rods. Then we also have an outlet pipe here. This will tend to remove away the condensed steam. And of course, we have the inlet pipe here. This pipe will be connected to the source of steam. It will let in the steam to cause or to eat up the metal rod inside the metal tube and cause it to expand. And we also have the metal rods here. Here we have the brass, steel, copper, and of course the aluminum. So this is one of the important apparatus that is required for this study. So the dial gauge, as indicated here, we see that it consists of two scales. We have the scales marked in black, and of course the scales marked in red. And inside it, you can see we have a small inner scale here, also known as the revolution counter. So the revolution counter will be used to show the number of rotations made for us to have a reading in the outer scales. So as you can see here, the pointer of the revolution counter is pointing 0 to show that it is still at 0 rotations. So the reading of the outer pointer, as you can see here, is 68. So to get the final reading of our dial gauge, we will take the reading of the revolution counter, that is 0. Then we'll add the reading of the outer scale, that is 68, multiplied by the precision measurement, that is 0.01 millimeters. So the reading will be 0 plus 0.68 millimeters. I mean, so that is how basically we are going to read our dial gauge. We'll come to see how it behaves when our metal rods are expanding after being subjected to heat. We also have other apparatus, that is the digital thermometers. So digital thermometers, we know that they include resistance temperature detectors, RTDs. They also include the thermocouple and of course the thermistors. So the working principles of these thermometers is that they consist of sensors that measures the change in resistance due to heat, and then it will convert this change in resistance to temperature. So this is the picture of what we called the digital thermometers. So we're going to see how it works when we get to the setup. We also have what we call an analog thermometer. Analog thermometer, of course, we know it consists of various parts such as stem, mercury, bulb, capillary bore, and of course the constriction. So the working principles of these thermometers are that as temperature rises or is when there is a presence of heat, the fluid expands along the capillary tube and the meniscus level is read against the calibrated scale. So that is how we are going to read our analog thermometers. We also have other apparatus such as the conical flask. Conical flask here will be used to hold water when we'll be heating to generate steam. And of course, we have the top cover of the conical flask known as the rubber stopper. This will be used to help us prevent or minimize the heat loss when we'll be heating water to generate steam. And of course, we have what we call a meter rule. So meter rule here will be used to take the initial and the final measurements of the metal rods. So, and also we'll use the meter rule to record the final measurement of the metal rods after they have been subjected to heat. So one might ask that why is it necessary for us to use or to measure the expansion with a micrometer screw gauge, whereas the initial length we are supposed to measure using a meter rule? What can be the reason? I think this is because a micrometer screw gauge or a dial gauge will provide measurements accurate to the nearest thousands of milliliters, or even smaller increments. As you understand that the basic concept of linear expansion that we want to determine at what increment do our material expand. And that is why we are using a diode gauge to show that small expansion is taking place. That is why it's necessary to use a micrometer screw gauge or a diode gauge to indicate this expansion. So also we note that the expansion of other certain materials or manifold rods can be very small and might require the precise measurements. In other words, ohmmeter rule, you know that it typically has markings at centimeters intervals, which means that the measurement made by the meter rule can only be accurate to the nearest centimeter. So due to higher precision, sensitivity, or ability to provide accurate measurements for small changes in length will require a diode gauge or a micrometer screw gauge. So that's what we are going to use. So we also have another apparatus here that is heater, because heater will be used to generate heat that will enable us to heat up water to generate steam. And we also have the three metal rods that we are studying. We have a steel, we have the brass, and we have copper. So these are the metal rods that we're going to use for this experiment. We're going to determine at what extent do they increase in length when they're subjected to heat. So the theory section of our study is that we find that when a solid bar of metal is heated, the increase in length is denoted as delta L of the material, and this increase in length is directly proportional to the increase in temperature, delta T. So, and also to the original length of the material, that is L1. So mathematically, this can be written as delta L is equal to the coefficient of linear expansion denoted as alpha times the initial length of the material multiplied by the change in temperature, that is delta T. And of course, where alpha is the average coefficient of linear expansion of the metal over the temperature range. But you know that delta L is nothing but the final length minus the initial length. So it is L2 minus L1. And of course, delta T is final temperature minus the initial temperature. So this is T2 minus T1. And of course, where L1 is the length of the bar at temperature T1, and L2 is the length of the bar at temperature T2. So when we replace delta L with L2 minus L1 and delta T with T2 minus T1, we see that our equation reads L2 minus L1 is equal to the coefficient of linear expansion alpha multiplied by L1 into T2 minus T1. Of course, T2 minus T1 is delta T, and L2 minus L1 is delta L. So when we make alpha the subject of the formula, we find that alpha will be L2 minus L1 divided by L1 into T2 minus T1. So this is the formula that we're going to use for us to determine the expansion coefficient for these metal rods. It's also good to write programs that will execute the expansion. That is, you can use a program in Python that will calculate the expansions and also other tasks that will be asked to do. So the procedures of this experiment is that we are going to first set up the apparatus using the first metal rod. You can start with brass, copper, or steel. So for this, we are going to start by a brush. So we can set up our apparatus as shown here. This is the outlet pipe, and which we said that it will tend to move out the condensed steam. And of course, here is the dial gauge that will show the amount of expansion when the metal rod is subjected to steam. And of course, here we have the metal tube that holds the steam. And this is the inlet pipe that will tend to bring in or letting the steam into the metal rod. And of course, here we have the digital thermometers. Here we have the conical flask, and this is the heater, and this is the analog thermometers. So it is always advisable that we set back the micrometer screw gauge from the end of the bar before heating process, or even after heating the metal rod. When you're setting this experiment, we must be able to create a space in between the dial gauge, or in between the micrometer screw gauge and the bar. Why is this necessary? We know that when the metal rod will be under heat, it could get heated up, and leading to incorrect value of expansion. Because when it is not set back, and the heating process is going on, the bar will get heated and will cause an expansion before the expected expansion. So that is why it is necessary for us to give a space or set back the dial gauge from the bar, so that at least we could create room for expansion. So before we could start the heating process, we are supposed to take the initial measurements of the metal bar, that is the initial temperature as T1, the initial length of the metal bar, that is as L1, and also the initial dial setting as E1. So as you can see here, before the metal bar was heated, the initial temperature T1 was recorded as indicated here. Then the initial length of the material of brass, was also indicated, was also taken using a meter rule and indicated here. And of course, we also had initial dial setting, that is before the heating process, was as indicated here. So yes, you are supposed to take these readings and tabulate them. Then we also are required to heat the water so that it generates steams, and allow the steam to enter the metal tube to heat up the metal rod, so that it can expand and even cause an expansion in the dial gauge. So the heating process is as indicated here. We have our apparatus set here. So this is water in the conical flask is being heated. Then this is the pipe that will let in steam into the metal tube, and this the one that will try to let out the condensed steam. And then when the heating process is underway, we'll see that the metal rod inside it will expand, and we'll see the reaction in the dial gauge. Then after that, then we are also supposed to record the final readings, like the final length of the metal bar after it has been heated, also the final dial setting, and of course the final temperatures. So maybe we can have a look at how the dial setting is changing when the heating is underway, and also we'll check how the temperature is rising when the heating is underway. So as you can see here, we have the final dial setting. So when the heating was in process, this was the reaction. So have a look at it. As you can see, the dial is moving, the dial is moving, the dial is moving, it is still moving. This shows that there is an expansion of this metal rod when it is heating up. So we can also have a look at how temperature was increasing when the metal rod was being heated. So this is the heat thermometer. As you can see, when the heating was underway, the temperature was rising as indicated. It is now 94.2, 0.3, 0.5, 0.6, 0.7. And of course, it will increase up to a point whereby it will be at equilibrium and it will start falling back. So we are supposed to record those readings. So now we are also supposed to take the the final length as indicated here. So it is as shown here. And of course, as we've seen the temperature rising, and it came to an equilibrium point of 94.8. So the reading was indicated. And of course, we had a reading of the dial, as we've seen the reaction. So the reading of the dial is as indicated here. So you're supposed to take these values and tabulate them. Then that would be the first heating process with the first metal rod. So we are also going to use another metal rod that is copper. And of course, we are supposed to follow the same procedures, that is taking up the initial measurements before we could fix in the metal rod into a metal tube and and allow it to expand when we introduce a steam to it. So the initial length of copper was as indicated here. As it was here, it somehow 56.8 centimeters. So you're supposed to record these initial measurements, and of course the initial temperature of the metal rod of copper as indicated here using a digital thermometers. And we're also supposed to record the initial dial setting, that is E1, as indicated here. Then we are also going to fix in the metal rod inside the metal tube and heat water to generate steam and allow steam to enter the metal tube and cause the metal rod to heat up so that we can see the expansion in the dial gauge. Then after that, we are going to take the readings, that is the final length of the metal rod when it has been subjected to heat, as L2 centimeters. And of course, the final temperature, as it will be indicated in the digital thermometer. As you can see here, it is 90.2 degrees Celsius. Then we are also supposed to take the final dial setting. As you can see, initially it was 68, but now it has increased to somehow 71. You know, it seems to have expanded. So the student is expected to record this length as L2. Then we are going to set up the apparatus again using the steel. We are going to fix in the steel inside the metal tube, then allow steam to enter the metal tube to heat up the steel, and we'll also see the amount of expansion using the dial gauge. So the same procedure we're going to follow by taking up the initial length of steel as L1, initial temperature of steel as T1, as indicated here, and of course the initial dial setting of steel as E2, as indicated here. Then we are going to heat water again and allow steam to enter the metal tube to heat up the metal rod. and we'll also see the expansion in the dial gauge. Then we'll also be required to take the final readings. This is set up of using still the heating process. So the final readings will be recorded as L2, that's the length of the steel in centimeters, as indicated here. T2 at the temperature of the steel, that's the final temperature. And of course, the E2, that is the final dial setting of the steel as it will be indicated here. So then the student is expected to do the analysis and come up with the conclusions that reflects the objective of the study. Some of the tasks that students is required to answer is as follows. The student is expected to use the equations in the theory section to calculate the coefficients of linear expansions of different metal rods. And also, as we have said, that student can also write a program to generate the coefficient of linear expansions of these metal rods, that is using Python. So the formula, as we had discussed in the theory section, was that the coefficient of linear expansion alpha is nothing but the final length minus initial length divided by the initial length times temperature 2 minus temperature 1. This formula will help us to get the coefficient of linear expansion for these metal rods, and also we'll be able to compare them with the theoreticals or standard values of linear expansion. The initial dial reading should also be indicated. Final dial setting as E2 should also be shown. We are also going to get the expansion of bar. Of course, we have, if we have the initial dial reading as E1 and the final dial reading as E2, so the expansion is just the final dial reading E2 minus the initial dial reading E1. So suppose it was a brass, we will take the final dial reading of brass as E2, then subtract the initial dial reading of brass as E1. Then that will show us at what extent as this metal rod expanded. And of course, we also get we shall also get the error in expansion of bar. The temperature difference, of course, if you have the final temperature and initial temperature difference will be the final temperature minus the initial temperature. And of course, we can also get the error in the temperature difference, the error in the value of the coefficient of linear expansion alpha. And of course, what would happen if the micrometer screw gauge was not reset back from the end of the bar? That is what we've discussed, so student can try to tackle it. And of course, why is it necessary to measure the expansion with the micrometer screw gauge, whereas the initial length of the bar can be measured using a meter rule? So there is some question that can be asked during the analysis. So this is all about linear expansion experiment. As we've talked about, it has many applications, like in riveting. The concept is highly applied. And also we guess that when we'll be analyzing the data and making a comparison, you will see that what materials is suitable maybe for buildings and why. You can give the reason why. That is, by giving a conclusion, you can compare your values with the standard or theoretical values from known sources, such as engineering books and also other books that gives the coefficient of linear expansion of materials. And remember, linear expansion coefficient of different metal rods can vary depending on the different types of the materials used, different temperatures, and of course, even due to experimental conditions that the material was carried out. So thank you for staying tuned. Have a nice time.